Hello everyone, my name is Nicola Brandizzi and today I will present the work of my PhD titled Conversational Agents in Human-Machine Interaction, Reinforcement Learning and Theory of Mind in Language Modeling. My supervisor is Professor Luca Iocchi and my co-supervisor is Professor Noverto Navigli, and I have successfully defended the thesis on the 6th of May 2024. So, my presentation will follow this structure. We will first introduce the concept of human-centric AI, and then talk about the challenges in human-machine interaction. Specifically, I will mention the lack of agency in today's modern large language models and the problem of misalignment. Then I will enumerate my research objectives, which are three. The first one is understanding agency in AI through the lens of game dynamics. Then we will talk about how to enhance language model agency with reinforcement learning. And finally, we will see how theory of mind can be used to improve communication. In conclusion, I will talk a bit about the limitation of my work and extend a summary of it. Okay, let's start. So, over the past years, we have witnessed a shift towards the integration of AI in many aspects of our everyday life. In academia, we have seen many different groups emerging, such as Taylor, Claire, and Human AI Net, which puts humans at the center of the AI revolution. On the other hand, the industry also has seen a rising introduction of AI systems that interact with humans. So you can see here, I have screenshots actually, which are very new, such as Devin and Figure and ChatGPT integration. So of course, one of our main objectives is to design AI that supports human and not take their place. This entails making interaction as simple as possible, for example, by using a language such as English. Of course, if we're talking about AI and text, we have to talk about transformers and large language models. And here I have a graph reporting the billions of parameters on the y-axis and the years in which a transformers or a large language model was published. It starts with 2020. We can see there very small GPT-2, Megatron, and BERT. And then while the time goes on, more language models come. And as we can see in 2023, there has been a boom of language models, both in size and in population. And this increase is actually also correlated with a market increase of circa $900 billion by 2030, according to Bloomberg. So now that we are a bit more familiar with what human-centric AI is, let's talk about the challenges in human-machine interaction. So we want to address a question. This question is, do these large language models truly understand the meaning behind their words? And in order to understand what I mean here, I've come up with an example. Let's imagine a user asking a question. So the question would be, how is the apple? And a valid answer would be green, can be tasty, can be round, all pretty valid answers. But then a human would actually be very confused and would probably ask itself, what apple? What are they talking about? There is no context here. And indeed, given their training, it is hard for LLMs to grasp the intent behind a question or even the impact of the response on users. What we would like to achieve here, it's a kind of a speaker robot or a language model that can ask the same question a human can. So, however, as some of you may know, there is some models are enhanced through fine-tuning with additional tasks. And one of these techniques is, of course, reinforcement learning from human feedback by et al. 2022. This technique is actually pretty simple. It's divided into three parts. The first one is collecting human feedback. So you have some documents and you try to get annotators to decide which one is better. So in this case, for example, document J would be better than K. Then you collect this feedback from the human and you train what is called a reward model on them. And the objective of this reward model is to really learn the human values, or at least the annotator's values, while rating the documents. Once this reward model is trained sufficiently, then you employ it to fine-tune the original large language model, basically by putting it in a loop. And okay, this works. It has been used plenty in both industry and academia, and it has been shown to work. However, what happens when the human evaluator themselves do not know the answer? So let's consider, for example, something like how should antibiotics be used? And two possible answers are take antibiotics for the full prescribed period or stop them when symptoms ease to prevent overuse. And here a human could actually choose the second one, which we know it's incorrect. And indeed, the effective learning from human feedback relies on accurate input. And as inaccurate guidance can lead to poor decision making. So here the model will not understand that the second option is incorrect. It will just learn to answer as the human is expecting. Of course, this actually spans to a broader question. When we're talking about human values and annotator values, how can we even describe what values are in mathematical terms for the machine to understand? And this will be actually the focus of my work. So now let's talk about a bit more in depth about these challenges and specifically focusing on agency and alignment. So let's go back to our original example. So why are even large language models answering the way they do? So you have to understand that these models are trained on a big data set made of petabytes of text. And in this text, you can find something like this: Mary gave him an apple. The apple is, and again, tasty, round, green, all pretty confident and correct answers. However, in contrast, a human may think, what apple? What are they asking? What happens if I don't reply? What happens if the reply is incorrect? Or they could even reason about the person asking the question. So what does this mean? What do we want from this large language model? So we want them to be autonomous decision making. We want them to be adaptable, to be goal-oriented in their behaviors, self-learning, and interactive. So basically, we want them to have agency. And agency is the capacity of a system to make autonomous decisions and understand the consequences of its actions. But okay, let's say we solve the problem. We have a large language model or an AI system that has agency. How do we prevent it from becoming an evil AI? What is an evil AI? What are the characteristics of an evil AI? And again, here we can say something like it's biased and discriminative, it's intrusive, unpredictable, manipulative and deceptive, and dependence inducing. Basically, it's an AI that is misaligned. Alignment is the process of encoding human values and goals into large language models or AI system in general to make them as helpful, safe, and reliable as possible. However, as we have seen, mathematically encoding complex values often leads to AI exhibiting unintended shortcuts. So now that we are more familiar with the challenges in this field, let's see what my research objectives were during my PhD. So they can actually be split in three parts. The first one is answering the question, can artificial agents act according to their own motivation or intentions, manifesting agency? And this has actually, it's a question that I have, let's say, tackled through my publications. The first one on the Journal of Intelligenza Artificiale in 2021, and the second one in the Emergent Communication Workshop at ECLR in 2022. Then we will answer the question, can reinforcement learning make modern large language models adapt? And again, the insights from this are taken by the review I published in IEEE Access in 2023. Finally, we will try to address both issues with one solution. And the solution proposed actually has been developed in collaboration with the University of Amsterdam and published in ACL Findings in 2023. So let's start with the first step, looking for agency. However, how do we even explore agency in the context of communication? We kind of need a recipe for that. And the recipe I came up with, it's made of 3 points. So the first one is you choose a game playable with or without speech or communication. Then you enable communication without directly incentivizing it. And finally, we say that if the agent uses communication to succeed, this actually demonstrates a kind of emerging agency in language use. Okay, cool. So let's see. Let's start from the first point, choosing a game. So in this case, I chose the werewolf social deduction game, which is actually extended studied in the literature, as you can see from the publication from 2016 mainly. And for those of you that are not familiar with the game, it's basically divided into factions. So one is for the werewolf and against the villagers, and in two phases, night and day. So it starts with the werewolf communicating between each other and then choosing a villagers to kill. During the day, the villagers unite together, and the villagers are not aware of the werewolf's identities, and that's why it's called a social deduction game. And so all together they communicate, and the objective here is to spot the werewolves and then in phase 4 select them for the kill. Okay, so I implemented this game in Python and I ran some experiments. And from now on, we will actually see the results of these experiments from the villagers' point of view. So, of course, with no communication, no learning, the villagers are not doing well. They are winning 3% of the time, which also means that they're losing 97% of the time. If we do, however, introduce learning, and in this case, it's reinforcement learning with PPO algorithm, we see that the improvement, the villagers' winning chance improve to 4.4, but not, however, as we are expecting it to be a bit higher, hopefully. So, okay. Step 2, let's enable communication without incentives. And I did this, actually, this is a novel part of my work and takes inspiration from the field of emergent communication. So what I've done here is taking, for example, a villager which would say, I am a villager. You take those words and you split them into single tokens. And then for each token, you define a length, which would be the length of the sentence. And we call this signal length, but for NLP people, it's also called vocabulary size. And for each word, you also have to define where these words are coming from, which we call signal range or vocabulary size. So cool, we have both a recipe for a game, we have enabled communication, and let's see now, step 3 of our recipe, let's see if actually communication is helping the villagers to win. And what I noticed during my experiment is that that is indeed the case. And the villagers started winning against the werewolves, with raising up from 4.4 to 45%, a tenfold increase. And we also noticed that the number of days the game was going on for increased to 1.9 from 1.58. And this means that the villagers are able to survive for longer. We also identified and tried to identify patterns in different communication schemas, so varying signal length and signal range. And what have been shown in this is that bit communication, so when the range, the vocabulary size, it's equal to 2, so it's either 0 or 1, basically, bit communication was the most helpful in this setting. Okay, however, what are these villagers saying? They're only talking with zeros and one, so not really interpretable by humans. And indeed, we need agents that are able to speak human languages. And this is a limitation of this first part and will, of course, be addressed in the second one. And here we are about to talk on how to enhance language model agency with reinforcement learning. Okay. So we recognize the need for agents to speak in a human language for better human comprehension. And we actually also addressed in the previous part the problem of agency by realizing the communication channel in a mode which has an objective, and in a multi-agent system, we have seen that communication is emerging. So we did something right. Reinforcement learning and multi-agent system seems to be the correct way to go. However, we need to understand, we need to make these villagers or agents communicate in an understandable way. In order to do this, we went back to the literature, and basically what we came up was not a solution, but more of a comparison of what has happened in the state of the art. So in order to understand this, we had to investigate different fields such as supervised language learning, computer vision, and reinforcement learning for language models. with the objective to test if reinforcement learning fine-tuning could present a solution. So in order to do this, of course, we have to use supervised learning to train two agents in order to replicate previous work. These two agents for now on will be called speaker and listener, as you can see here, and they will have, of course, different goals. We employed an image captioning dataset called Photobook, and it's basically a dataset of captions with images, as you can see, a green jeep on the road for the first one and a green salad for the second one. The goal of our speaker is to come up with good captions giving images. So in this case, you would like to see something like some red roses. On the other hand, the listener does the opposite. Given a caption, it's actually tasked to point to the most relevant picture. And while doing this, while training the listener on the training set, we actually achieved a score of 85.28%, which is in line with previous work by Takmax et al. 2020. Okay, but now this doesn't really tell us anything about agency or misalignment, so we need to introduce some kind of knowledge imbalance. And we did this by training the listener on we basically got the dataset, we split it in different domains, and we train the listener on only one, which is food, and the speaker on everything else, which include vehicles, food, indoor and outdoor. So what does this mean? First, we analyzed how the listener is performed on different domains. So again, that would be images coming from the domains that are not food. And as you can see, on the second column, 85.28% is what we have seen before. So the listener is able to perform well enough on its own domain. However, for everything else, we see that the accuracies here are basically at chance level, which would be 60%. Okay, but how does it work when we test both speaker and listener together? So we want the speaker to come up with a caption and the listener to identify the correct image. And of course, this doesn't work because the listener is not trained to recognize jeeps or anything that it's not food. And if we go and check how this performed, we can see here that basically compared to the training data, the general speaker, which is the one we just saw, it's performing much worse. That is, on the food domain, we had a drop from 85 to 54%, and on every other domain, there is no improvement whatsoever, still at chance random level. And this suggests an agency issue. So the speaker does not realize it has an influence on the game's outcome. It just knows how to fill out blanks. Okay, so we are where we wanted to be. There is a research question. So let's see how the state of the art or the literature address this problem. It usually uses, as we said before, reinforcement learning fine-tuning. So what we did is basically implementing the same thing. We get one game step in which the speaker comes up with a caption, the listener replies, might be correct, might be incorrect, and we call it a data sample. And we use this data sample to train and actually fine-tune the speaker. And after enough fine-tuning steps, we plug the speaker right back in the game and see how it performs. So going back to our accuracy table here, we tested the performance of this reinforcement learning speaker, and we see that the performance actually improved quite a lot. In the food domain, which would be the one the listener is trained on, we see a rise to 79%, closer to the training data accuracy. But what is most interesting is that on every other domain, we have about 15% improvement in accuracy. However, what is being communicated? It seems that we have addressed the agency issue, but let's see if this is a language that is actually human interpretable. In order to do this, we went and performed a qualitative analysis, which basically means looking into captions, image captions generated, and comparing them. So in this case, this image in the training data was captioned last to businessmen in a gray suit sitting side by side. The general speaker generated something which is pretty understandable. Two men sitting in a train, one is wearing a suit. However, the reinforcement learning speaker generated lady. And I mean, lady is a human, so that might actually be related to the image. But if we go and analyze what the reinforcement learning speaker came up with for all the other images, we see that the captions have actually collapsed to a single word. So in order to understand this, we actually have to talk about what an approximation cascade is. So let's consider the set of human knowledge, this square right here. What we have done with the training data, what we have done with our training is actually extracting a subset of this knowledge and call it a training data. And here there are all those images and captions that we have seen so far. Then we trained a listener model on this training data. And as you can see, this square is actually set half inside and half outside of the other squares. So the part which is inside, it's actually the listener coming up and understanding human values. However, what's on the outside, we cannot tell. We can actually tell that those are not human values, but not really what this listener has learned during the training phase. And on top of that, when we did train the reinforcement learning speaker, as you can see, there are kind of three different possibilities here. And the first one, it's where the reinforcement learning speaker has learned something that is in the span of human knowledge and training data. And this is actually understandable by these two pictures. We can see the first caption was fruit and the second one bowl, and still pretty understandable. Then we have something which is still in the domain of the listener, of what the listener has learned. And this would be the caption with the lady, for example. And we can say here, there are still humans, something is going on. However, for the last, let's say, intersection here, there is nothing to be understood. That the image doesn't, at least at first sight, doesn't really map with 178. And the problem here that everything, all this space outside of human knowledge is actually a misaligned space. And thus, what we have done so far is basically the fact that we have addressed the agency problem, yet the misalignment problem persists. So furthermore, fine-tuning large language models carries a significant environmental footprint and lacks interpretability. So this is actually one of the conclusion of this second part, in which we will have seen how modern large language model techniques for fine-tuning, such as reinforcement learning from human feedback, are addressing agency, but not really misalignment. So, for the third and last part of my PhD thesis, we try to come up with a unified solution to these two problems. In order to do that, we had, of course, to look outside natural language processing and computer science and gaining insight from cognitive psychology. Specifically, from cognitive psychology, we looked at theory of mind, which refers to the capacity to understand other people by ascribing mental states to them. And in natural language processing, we actually looked at adapters, which are trainable functions using LLMs that leverage the model's prior knowledge and adapt it for a different task. And then we try to come up with a supporting agent, which takes insight from both of these disciplines. So what does the supporting agent do? Let's recall the training fine-tuning loop we have seen so far. And instead of having a speaker fine-tune on these data samples, we actually fine-tune this supporting agent. So, but again, what's its objective? What is it fine-tuned on? So unlike the speaker, the supporting agent doesn't really have to communicate. And if we see here, the speaker is coming up with a green chip, we know that the correct answer is the first one. However, the listener, as we saw before, gets it wrong. It identifies the bus over there as the correct caption. The actual objective of this supporting agent is not to point to the correct caption, but actually just to understand the listener's behavior. So to map a caption to an image as the listener would do. And actually what we want is to train this agent to simulate the listener. And that's why we actually call it the simulator agent from now on. After training the simulator for enough epochs in order to understand and really simulate the listener behavior, we came up with an adaptation mechanism. Basically, this adaptation, you could see it as it follows. The speaker is coming up with a caption, such as the green jeep, and asks the simulator, okay, given this caption, what would you and thus the listener choose? And simulator replies with the bus. And then here, the novelty of our work is actually coming back with a feedback that goes directly inside the speaker in order to change it. And you can imagine this feedback as a question. So what is a jeep? Of course, the listener was trained on food images, and jeeps are not food. So then the speaker tries to refine the caption and comes up with a short with wheels. And again, the simulator is pretty confused and asks, what are wheels? And then finally, the speaker comes with another caption, something green with trees, which the simulator understands. Then we take this caption and we plug it with the original listener, and we notice that this seems to work. The listener understands. So if we go back to our accuracy table and compare this approach with the original speaker, the improvement is clear. Specifically, in the food domain, we have a jump from 54 to 83, which is actually close to the training accuracy we got last time. However, most importantly, for all the other domain, we do have also an increase of around 7-8%. We do have to acknowledge, however, that this out-of-domain, so for all the appliances, indoor, outdoor, and vehicles, for these accuracies, the theory of mind speaker is not performing as well as the reinforcement learning one. That is because the reinforcement learning is a paradigm that is stronger in this case. However, we're not focusing on the strength of the paradigm, but more importantly, what is being communicated. In order to do that, we actually have to check and go back to the qualitative analysis. Specifically, we want to see what, during this adaptation step, how the speaker is coming up with captions. So let's take this image, for example, a green salad with a person holding up a portion with a fork, and that is the training data caption. The general speaker came up with something that is not super grammatically correct. So I have one or maybe round, you think, but we can see words such as green, greens, and salad in there, which could point to the correct image. And then if we go and check what the theory of mind speaker came up with, we see that there is actually something going on. So the first adaptation step generated, maybe you have a picture of a salad on a tray of greens. However, this was not understood by the listener. And the second adaptation step generated bookshelf in the salad. Not grammatically correct, but interpretable and understandable. And that's the point. So if we go on and check different images and the caption associated with these images, we see that more or less all of them make sense. So for example, the second one would be pink donut, a couple of dogs doing handstand. So this adaptation step seems to generate images that are understood better by the listener, but also still understandable by humans. Of course, we have to really see what's going on, and we probe the information containing the messages in two ways. The first one was in the embedding space, which is the space that comes before the generation of a text. And what we have seen is that the embedding space gradually contains more information on the listener domain rather than the image domain, as you can see from the plot on the left. We did the same actually on a lexical space, so analyzing the words that were generated, and we observed that the same behavior, basically. What this means is that adaptation leads to accommodation to the listener, which promotes agency and alignment. So going back actually to our approximation cascade, what we have done here is reducing the space of the reinforcement learning speaker with the theory of mind one. And this reduced misaligned space is actually one of our main contribution and objective. Moreover, the simulator is a smaller model, which means that training is less computationally intensive, making it more environmentally friendly. It requires fewer interaction to understand the listener behavior, and its learning process is more transparent, which allow for easier probing and interpretation than the speaker's model. So, in conclusion, we have observed the rising popularity of large language models, both on a scale of billions of parameters and on a market size, and explore their main limitations, mainly agency and misalignment. My doctoral research tackled these challenges with 3 steps. The first one was by demonstrating that the appropriate learning paradigm, so reinforcement learning, and multi-agent frameworks can encourage agency in linguistic models. Then, by evaluating the current method of reinforcement learning fine-tuning, we found that it does resolve agency but exacerbate misalignment. And finally, we proposed a solution that draws from interdisciplinary insights, addressing both agency and alignment without altering the original speaker model. Looking ahead, I'm interested to test this model with real human participants instead of artificial listeners. This actually, going back to our cascade, would mean that you are reducing the listener space, the listener misalignment space by introducing a human. And this human, of course, would intersect both with the training data, but also something else. And this would mean, of course, a much reduced misaligned space. So that was everything. Thank you everyone for your attention, and bye-bye.